All right, guys, we got some serious stuff going on in this section. So we're looking again at finding volumes of solids that are generated by rotating about different lines. Okay, and we're looking at a different method. So let's look at, I just want to look at this region really quick and kind of talk about why it would be difficult maybe to do washers or discs. But I know you've read through the book and the development of this, but I want to do a couple examples for you, and that's going to be how you really understand this. Of course, look at your examples in the book. I'm trying to do different examples so that you have not only the examples in the book, but these examples as well. Because the thing about math is to get good at it, you just have to do it a lot. And you have to see a lot of examples until finally maybe it'll kind of click, right? So I'm going to get an XY plane going here. What we have here is we have a region bounded by a couple of things. We're going to be bounded by the x-axis and the graph of f of x equals 3x minus x squared. So I want to look at what that graph kind of looks like. I know that this is a parabola facing down. Like one thing that I always kind of do when I'm looking at, well, how am I going to graph this and figure out what the graph of this looks like, is I could take an x out, right? And I would be left with 3 minus x. So what do I know? I know that I'm going to go through the x-axis at x equals 0 and at x equals 3. So this should be something you're able to do. You're in calculus 2. You should be able to graph this. Even without a graphing calculator, you should be able to graph 3x minus x squared. Again, how do I know it's a parabola? Because of the squared, right? How do I know it's facing down? Because of that negative. And then I could plug in maybe some numbers between 0 and 3 to kind of see what happens. So let's go ahead and sketch this region. And then I'm going to attempt to draw this for you. I am going to draw this for you. And this is going to be a nice lesson in imagination. All right, so here's my XY plane, not perfect. I kind of made the tick marks myself, but let's kind of see what's going to happen with my solid here. So my solid, my initial region, right? I know it's 0 at 0. I know it's 0 at 3. And then if I just plug in some points, right? So like when x is 1, I get 3 minus 1, which is 2. So I know that at 1, I'm up at 2. I know if I put in 2, then I get 6 minus 4, which is 2. So at 2, I'm at 2. So that means that the kind of the vertex of my parabola must occur somewhere in between there. I don't actually care exactly where. I could figure that out, but that's what my graph looks like. And I'm going to take this graph and I'm going to revolve it around the y-axis. Okay, so one thing that you should have recognized between this section and the last section is that if I am revolving about the y-axis, then I'm going to be integrating with respect to x. It's always the opposite of the whatever axis you're revolving around. Let me say that again. So whatever axis I revolve around, I'm going to be integrating with respect to the opposite variable. This is not true with discs and washers, okay? If I was rotating about the y-axis with a disc or a washer situation, I'm integrating with respect to y. It's different with the washers, or excuse me, the shells, okay? So I'm gonna rotate this about the y-axis. That means I'm gonna get kind of a reflection over here, right, of all of these points, you guys. I'm gonna apologize right now. I'm not great at drawing this like on paper, and on the computer screen it's even worse. But I revolved that. Oh shoot, I didn't want to do that. I revolved that, and what this gives me is it makes me think of like a bundt cake. Have you guys ever had a bundt cake before? To revolve this around, and I get kind of this bundt cake looking thing, or I like to think of it as like a mountain chain in a perfect circle, right? With like a crater, like a lake at the bottom or something. So, all right. So again, the idea of these shells is, what if I had taken a strip, right, in my original area here, and I took that strip and I revolved that strip around. So what I'm going to get then, if I take that strip, and this is just at some y value or some x value, excuse me, right? And if I take that strip and I revolve that around, oh, do you see it? I get this shell looking thing, right? That's what your book talked about. I get this shell looking thing. And then, as is the case, oh, guys, that's not horrible. As is the case with everything in calculus 2, is if I took a if I decided to take, you know, a slice here, let's go over here. If I decide to take a slice here, then I'm just going to get this other shell. I'm going to rotate this shell around here, right? And it's going to kind of sit outside of these. It's like a Russian nesting doll where these shells, right, kind of sit within each other. So like this red shell is going to be kind of inside this green shell, and I'm going to just have these shells stacked out to get the volume of this solid. And if I can figure out the volume of one of these shells, right, then I could add up an infinite number of them, and you can see kind of why we integrate with respect to x. If you notice, I'm stacking up these shells right in the x direction. They're going to be kind of nested inside each other in the x direction. All right, so I know you got the formula for this, but how are we going to do this? So let's look at that kind of pink shell there that I have, right? So here's my shell, and the way I like to think about this is if you took like a soup can, right, and you took that soup can, and let's say you cut it down vertically one of these sides, and you opened it up, right? Basically what we're finding is the surface area of the cylindrical shell, because the width of this shell, like any width that it's going to have, is just going to be my dx, because I'm going to have so many of them that it's basically going to be negligible, the width of those shells. So what I want to figure out basically is, right, if I cut it right here and opened this up, took that out, and if we were in a real life class, I would show you with a piece of paper. If you take a piece of paper and make it into a tube and then open that tube up, right, you get just a rectangle. So let's figure out how to find the area of this rectangle right here. Well, if you look at this shell that I have right here, right, has gone through the XY plane. And I'm just going to say that this distance right here where I took this shell is just X. So what is the radius of this shell then? The radius of this shell is X. And when you open this up, this distance right here is just going to be the circumference of I want to be able to show this to you a little bit better, but it's just going to be the circumference of that circle right there. And we all know, of course, that circumference is 2 pi r. So in this case, that's 2 pi x, because my r is just x. Yeah, this isn't too bad, right? And then what is the height of the shell? Well, look at the height of this. If I'm starting at x, right, the height, I'm just grabbing all of these shells and grabbing them along this blue line right here. What is this blue line given by? It's given by my function. So whatever my x value is, the height of my shell is 3x minus x squared. Okay, so how do I find then the area of my shell? Basically, I just know that the area of a rectangle, right, would be 2 pi x times 3x minus x squared, because length times width is area. And then the volume of the shell we get by multiplying by this little dx right here. Isn't that great? I love doing these. And I have to say, I don't think my picture is horrible. It's maybe not the best thing in the whole world, but it's not horrible. Wait till you have me for Calc 3 when we take calculus and we put it in 3 dimensions. Oh man, it is seriously a lesson in imagination. Okay, so I'm not going to put my bounds quite yet, but what I'm going to do is I'm going to add up an infinite number of these shells, right? So the only way we can add up an infinite number of things is with calculus. So I have the dx there, right? This right here is the volume of one of those shells at x. So remember, this x right here represents where we're taking those shells. And I'm gonna, again, what we did, ooh, look at these really cool colors here. I took a little slice and then I rotated it around. And I took a slice here and rotated it around. I could take, isn't that a cool color? Another slice here, another slice here, another slice here. And I'm taking these slices and I'm rotating them around and they're making these shells. So where can I take these slices from? I think I have a little bit. I think I might have a little bit too much here, but I can take these slices from here to here, right? Wherever my original function was. So what am I going to integrate from? I'm going to integrate from my original r, where I can take those slices, and I can take them from 0 to 3. I hope that makes sense, right? I don't actually want to go from -3 to 3 because this whole part of it right here, that part is taken care of when I do that revolution. What you want to think about from the 0 to 3 is where can I take these slices in the original region, and then I'm going to rotate those slices. Okay, I hope that makes sense. That picture is just beautiful. I don't care who you are, that's a beautiful picture. I'm going to take the 2 pi out. Let's do some calculus now. These actually are not super hard to integrate. We'll see when we get to arc length and surface area. The integral can be kind of confusing because the square root comes in. But for right now, these actually aren't too bad. Antiderivative of 3x squared is x cubed. Just like you saw with discs and washers, the hardest part about these is just going to be actually setting up the integral, right? That's going to be the hardest part about these. So I get 2 pi times, let's put in the 3, that's 27 minus 81/4, I think. Ooh, I don't know what that is exactly. And then when I put in the 0, I sure enough, I do get 0. And then let me see if I have the answer here quickly. I think it's 45 pi over 2. But you should check me on that. I think that's correct. No, that might not be right. Let me hold on one second. Oh yeah, that was wrong. Sorry about that. It's 27 pi over 2. 27 pi over 2. Right? Or 13.5 pi, or whatever 13.5 pi is. And that's my answer. Now, why are shells important, and why do we even need shells? Well, if we looked at, I can't go back to that picture again. But if I had like a function, a bundt cake like this, right, on my XY plane, that was a pretty good fast drawing. Here's my bundt cake here. If I tried to do discs or washers, we'd have some issues. I could do that. If I rotate about the Y, then I'm going to be integrating with respect to Y, right? So I could look at a washer here, but look at what the radius is going to be. This is going to be quite complicated. The radius here, my outside radius, right, is a half of my function, but then the inside radius is the other half of the function. Plus I'd have to have it in terms of Y because I would have to integrate with respect to Y. So it just gets to be kind of difficult. If I look at a slice here, it's not even going to be a disc. So we have some issues, right, if we tried to do washers on this. And so that is why the shells are always, I know they look a little bit more complicated, but they actually allow us to find volumes, sometimes in a way that is easier than if we were to do washers. All right, let's do another example. All right, let's look at this last example then. So we have, let's let R be the region bounded by y equals the square root of x, the x-axis. So here's what we're bounded by. Square root of x, the x-axis, and the line x equals 4. Find the volume of the solid when R is revolved about the x-axis. So right away, I know I'm going to be integrating with respect to y because it's always the opposite, remember? It's always the opposite of whatever we're revolving about, right? Or perpendicular to whatever, parallel to whatever we are revolving about. All right, so I'm gonna draw a quick picture of this. So I know I'm going to x equals 4, so I'm just gonna kind of estimate here 4, and I'm gonna do square root of x, right? So I know that at 4 it's at 2. So let's see what is gonna happen here. So I have at 0 is 0, square root of 1 is 1, and I'm bounded by the x-axis, right? So I know I'm not gonna go below that, and then I know I'm up here at 4, so I know I have something like this. So that's the region, and we're going to rotate it about the x-axis. Okay, so I'm going to, not do that. I'm going to create a couple boxes down here, and this one's going to be, so let's look at that region right there. So because it's the x-axis, you got to kind of think about this a little bit, but this is the region that I'm rotating. Okay, if you look in the book at another example that they have, and instead of having x equals 4, they have y equals 2 is the other region, and then this would be the region that I'm rotating. So it could be different, right? So just make sure you understand really what is being bounded and what you're going to be using for that rotation. So I'm going to rotate it about the x-axis. So I'm going to come down here I'm gonna come over here, right? And I'm gonna get kind of this bowl looking thing that's really useless because it's a solid. But you know, whatever. I want to get the volume of this thing right here. Now, of course, discs would be easier to use, but I want to show you how to do this with shells. Okay, so discs would be easier to use. Yes, I will give you that. I could just slice this guy pretty easily and I would use the disc message easily, but I want to look at method easily. Let's look at what would happen if we wanted to do this with shells. So remember, this is the area I'm looking at. I want to take a little slice, right, of this shell right here. It's going to be bounded right here by that x equals 4. And if I rotate that about right here, right, I'm going to get kind of the same thing, but it's going to look like this. Again, I'm taking a slice of the original area, right, and I'm going to get this shell looking thing right here. I hope you can kind of see it. It's going to come out like that. Oh, that didn't go so well. But I hope you can see that I'm kind of using these shells to make this solid. You know, if I had picked maybe something down here, I would have gotten a shell that looks a little like this. You see it's a little skinnier and longer, and that kind of makes sense, right? Because I'd be on the inside and I'd get this shell looking thing right here, and it'd be kind of nested inside that other shell. And so I'm just going to keep going right along the y-axis here, and I'm going to just keep taking little strips of this region and I'm rotating it about the x-axis. Hope that makes sense. So again, whenever I do these, every time I do these, and I've done these a long time, I always kind of draw myself a representative shell. So I know I have this shell that looks like this, right? If I look at, and that's a basic idea of it. Well, what if I took it and I cut it right here and I kind of opened up the flap here and opened up the flap here? Then I'm going to get this rectangular looking sheet, and it will have kind of a little bit of a width, but remember that width we're just going to call dy. And so what I really care about is what is the area of this kind of sheet looking thing? Well, I know that I'm going to say that this distance right here, I went and grabbed that slice at some height y. I don't know what that y is, but just some height y. And then when I open that up, it's just going to be 2 pi y for the circumference of this circle right here. That's that length that I get when I open that circle up. So now kind of the hard part on this one is figuring out this part right here. So if I want to figure out this distance right here, right? Well, if I want to know this distance, I know that this whole distance here is 4. It must be, right? Because that's what I'm bounded by, this x equals 4. And then what is this distance right here? Well, this distance right here lies right on the graph of my function. So the graph of my function is y equals the square root of x, but in this case, I want x to be my dependent variable. I want to plug in the y and I want it to spit out an x value. I want it to spit out this horizontal distance right here. And so what is that going to be? It's going to be y squared. So what is this distance going to be? It's going to be the difference between 4 and y squared. So it's going to be 4 minus y squared. That's going to be this distance right here, which in turn is the height of that shell that I have. I hope that makes sense. So what is the area of this then? It would just be 2 pi y times 4 minus y squared. And now again, that was the hard part. Look at that beautiful picture that I have. So my volume then, I'm just going to take the 2 pi y, that's the circumference of my shell, times the kind of height of my shell on its side, right? And then times the width of my shell, which is just dy. Now, where can I take shells from, you guys? Where can I take shells from? Let me see if I can get a different color here. I can take shells from any of this original region, right? I'm going to be, whoa, I went a little too high there. Sorry. So where is the original region I can take this from? Well, my original region right here, right, just went from 0 to 2. So that's where I can grab those shells from. That's where I can take those little slices, right, of my region. So I'm going to go from 0 to 2 pi y times 4 minus y squared. promise I'm almost done. We're almost at 20 minutes here. So I'm going to get 2 pi. We're going from 0 to 2. This is the easy part. 4y minus y cubed dy. Okay, so I get 2 pi times 2y squared minus 1/4 y to the 4th. I think this is going to be pretty nice. 0 to 2. So that's 2 pi, right, times 8. Minus, this is 16 divided by 4, which is 4. So it looks like we get 8 pi total for my answer. Makes sense? Would disk method have been easier? Absolutely, the disk method would have been easier, but it wouldn't have been as much fun because you know what? It's just really fun to do these shells. Don't you think? I think so too. I know this can be difficult. If you guys just watch those 2 examples and you need more, just holler at me and I'll record you more examples. Yeah, you're welcome. Anytime. All right, you guys, have fun.